up, we have Gia speaking. Sorry we're running a little bit behind, but hopefully we'll pick up a little bit of lost time.
Okay. Thank you for introducing me. Hi, everyone. My name is Gia, and today I'll present our recent work on UniSparse, which is an intermediate language for general sparse format customization. This is joint work with Zhongyuan, his postdoc in our group. Zijian, he's in Peking University. Ben, Hongbo, they are in Intel, and my advisor Zhu. The volume data is increasing at a rapid speed in our era, and at the same time, a noticeable trend is that much of the data contain redundant values and they are sparse in nature. So the sparse data are pervasive among various domains. If we roughly analyze the density of non-zeros for domain-specific data, we can observe that a lot of application domains involve sparse data computation, including poor neural networks, graph learning, graph processing, and scientific computing domains such as computational pangenomics and electromagnetics. Though sparse data are pervasive, most of them are being processed in their dense forms. If we take a look at a simple matrix vector multiplication example, it requires only a few lines to implement the kernel if the matrix is in its dense form. However, if the matrix is in a sparse format, say the compressed sparse serial format, which is the CSR format, it becomes more challenging to implement a very simple kernel because the data structures are becoming more complicated and it requires substantial domain-specific knowledge for programmers. Therefore, processing sparse data in their specialized formats introduces a great challenge of programmability. And at the same time, researchers are proposing new formats not only for the CPU platform, but also for other platforms such as GPUs, FPGAs, and ASICs. The trend of heterogeneous computing introduces a great challenge for portability as well, where the implementation of a sparse format varies a lot from one platform to another. All of these challenges drive us to think about building an automated compiler to handle the complexity of sparse formats. However, automatically generating sparse program is a hard problem if we consider the vast variety of sparse formats. Let's start from the basic formats. If we store this example sparse matrix in memory, the most straightforward way is to store only the non-zero elements corresponding to the data of this matrix. Of course, we need to store the positions of the elements as well, and the straightforward way is to write down the row and column indices, which are the metadata of this matrix. And this format is called the COO format. We notice that in COO format, we store row and column indices in separate arrays, and this can be described as an structure of arrays layout. On the other hand, the other format, DOK format, it adopts an array of structures layout. It basically stores one row index, one column index, and one data element in a tuple, and there are 6 tuples in this example. So these are various memory layout options. If we take a further look at the COO format, we notice that there are consecutive repeating row indices, meaning that it can be further compressed. We can add a row pointer and remove the repetitive row indices. And because the row index array contains row indices from all the rows, we can omit it, and we will get the CSR format. We observe that there are still consecutive repeating elements in the row pointer array of the CSR format. And this is actually introduced by the empty row, which is row 3 in this example. So if we remove row 3, we will get a more compact format, which is the doubly compressed sparse row format, short for DCSR format. The DCSR format is more space efficient and is especially suitable to store matrices with many empty rows. Now we get a flavor of how sparse formats can be increasingly customized, but actually the variety of formats is far beyond the layout and the compression schemes we just talked about. There are hybrid formats where a matrix is decomposed and each submatrix is stored in their own format. There are also formats that are specialized to hardware platforms. An example is that over 70 formats have been proposed purely for the GPU platform. And other examples include specialized formats for accelerators. To support such a rich diversity of formats, we need to think about a new abstraction that can cover general format customization. In this work, we propose UniSparse, which is a unified abstraction for sparse formats. The key idea of UniSparse is to express a sparse format separately in its data structure and data layout. The data structure of a sparse format indicates how data are logically represented, and UniSparse adopts a metadata tree to visualize the data structures of a format. And data layout indicates how data are physically represented in memory, including various layout options such as array of structures and structural arrays. We firstly take a look at how UniSparse supports various memory layout options. If we write down row and column indices in a tree form, we can get an equivalent tree representation of the data structures in this sparse format. And there are many ways to store this tree in memory. If we do a breadth-first traversal of this tree and write down row and column indices as we visit the nodes, then we will get a structural array layout, which corresponds to the serial format. And similarly, a depth-first traversal of this tree can yield an array of structures layout, which is the DOK format. UniSparse uses a pack primitive to mark the dimensions that we store as an array of structures layout. And the dimensions that are not marked with the pack primitive are by default stored in a structure of arrays layout. Next, we introduce how UniSparse expresses the data structures of a sparse format using index maps and mutation primitives. The index maps indicate how index iterators of a sparse format are calculated from the regional index iterators in their dense form. For example, for the diagonal format, the offset of diagonals are calculated as the difference between the column iterator D1 and the row iterator D0, while some major dimension is simply the row iterator D0. The index expression can also be custom index maps, where we use an indirect keyword to mark the dimension, and the details of how the new iterators is calculated will be specified in a function. The custom index maps allow us to express irregular formats, such as the CISR format. In CISR format, what the indirect function do is basically schedule rows of this matrix into two partitions in a load-balanced manner. So we have talked about supporting index maps. How do we express different compression schemes? In UniSparse, we introduced two mutation primitives for format encoding. The first mutation primitive is the merge. Merge takes in one dimension level number, L, and the semantic of merge L is to fuse all repetitive paths from the root down to the specified level L in the metadata tree. We use the CO and DOK as an example. If we do apply merge at the row dimension, then the repetitive row indices 2 will be merged into one row index, and the children nodes at this column dimension D1 will be inherited by the result of the merged row index node. And this finishes the merge primitive. After applying merge, we get the DCSR format. The other mutation primitive is called trim. The trim primitive takes in two level numbers, S and E, where S means the starting level number and E is the ending level number. Trim of S and E will remove all zero values identified by the indices at the ending level of E and up to the associated metadata up to the starting dimension level S. We use the metadata tree of the CSR format as an example. If we apply trim of both S and E to be the row dimension, then the empty row index 3 will be removed. And we also end up in the DCSR format. We have already seen how mutation primitives affect the data structures of the metadata tree. In UniSparse, the mutation primitives merge, and trim can be used to encode sparse formats with the dense format as the origin point. If we further introduce reverse operators of merge and trim, which are split and fill in UniSparse, then the combination of these operators can convert an arbitrary format to another. And to automate this format conversion process, the compiler only needs to infer and generate a sequence of conversion operators. And this is basically how UniSparse performs automatic format conversion. We implement UniSparse as an intermediate language in the MLIR infrastructure. The top box shows format encodings, which are attributes of tensor types. And the middle box shows two format preprocessing operations. The decompose operation splits matrix into two submatrices, and each will be converted to their own formats. And the format and the conversion and the convert operation performs automatic format conversion. The bottom box specifies the compute kernel using a versatile lineage.generic operation. The right-hand side shows the code generation process. The compiler firstly infers the data structures and the layouts of the from the format encoding, and then the format customization operations are lowered to a function call which will be linked to an implementation in a library. The lineage.generic operation, which specifies the compute kernel, it's either lowered, leveraging the MLIR Sparse tensor dialect and run the lowered code on the CPU, or lowered to a function call to link, and which will be linked to a library to execute on other hardware platforms. We firstly evaluate the format conversion performance of UniSparse, and baselines include TACO and the MLIR Sparse tensor dialect. As for coverage, UniSparse supports more conversion cases, especially for custom formats. As for performance, the execution time I listed with respect to as a normalized number with respect to the performance achieved by UniSparse, and the exact runtime are included inside the parentheses. We observed that UniSparse achieves comparable performance with the two baselines for the conversion cases that they can support. We also use UniSparse to evaluate highly customized formats. We use UniSparse to generate a high-performance hybrid format for a heterogeneous CPU and GPU setting. Specifically, we use UniSparse to decompose the input matrix into two submatrices, and one submatrix is converted to the block diagonal format, and the other is converted to the CSR format. And the heterogeneous setting with one submatrix running the SPMV kernel on CPU and the other running on the GPU achieves the best performance over several baselines. One baseline is running both submatrices on a CPU, and the heterogeneous setting achieves 5.63x speed up over the homogeneous setting. Another baseline is running is the Sparse implementation of the SPMV kernel using CSR format running on GPU. Our heterogeneous setting achieves 1.28x speed up over this baseline. And the last baseline is running a highly optimized MKL implementation of the SPMV kernel using CSR format on the CPU, and the heterogeneous setting achieves 10.73x speed up over this setting. We also investigated high-performance formats for a GPU platform. We use UniSparse to generate a hybrid block LPAC and a CO format with the matrix decomposed into submatrices, one converted to the blocked LPAC format, and the other converted to the CO format. We run the sparse matrix multiplication kernel using the hybrid format on the NVIDIA GPU. The baseline is the Sparse implementation of the same kernel using only the CSR format. And using the customized format generated by UniSparse, the SPMM kernel is getting 2.7x speed up over the baseline. We also use UniSparse to generate banking formats and evaluate their performance on the simulated PIM device. As introduced early in this talk, we leverage custom index maps in UniSparse to generate the CISR format with a load balancing strategy. However, we find that by reordering the rows according to the number of non-zeros and schedule the rows with the heaviest workload first, the format actually achieves better performance. According to this observation, we created a new format called CISR plus format using UniSparse. We profile the workload distribution on the simulated PIM platform with both 1024 and 2048 PIM cores. And we have several observations. One is that the imbalance issue becomes more of a bottleneck with a greater number of PIM cores, since each PIM core will have a fewer number of rows and less workload. And another observation is that the CISR plus format achieves the best workload balance compared to the other two formats. And here shows the performance comparison of the SPMA kernel using these three formats. And the CISR plus format achieves the best performance over the other two formats due to the most balanced workload among the PIM cores. With all these custom formats generated by UniSparse, we demonstrate the powerful expressiveness of UniSparse format abstraction and the productivity and performance benefits of using UniSparse to perform automatic format customization and compute kernel generation. With that, I will conclude my talk, and I'm happy to take any questions. Yes.
Hold on. Oh, okay. So I saw a lot of your experiments were on format conversions, but you also had SPMM. I'm wondering if you could give some intuition to how you generate the tensor algebra algorithms like tensor contractions and additions and things like that based on your merge primitives and such. And what kind of generality you have in what kind of tensor algebra expressions you can generate code for with what kind of operands.
Our compiler firstly infers the data structures and layouts, basically how the tensor are stored in memory from the format encoding with those like index maps and the mutation primitives. And then we leverage the MLIR Sparse tensor to generate code because we already know how the tensor is stored in memory so that we can interface with their...
So this, the Google sparse tensor dialect? Or?
Yeah.
Oh, okay, so you can take your descriptions of operations and you can turn that into the kind of format language they have?
Right, yes.
Okay,
yeah.
Thanks.
Thank you.
Okay, well, apologies, I cut it at one, running a little bit. Oh, let's take the question from Olivia while you get set up.
I had a really minor question about, you said so for some of the reverse transformations from like filter and merge, they seem pretty straightforward, but in terms of for fill, how do you selectively fill? Because in your example, there was only 1 0, and instead of filling, let's say, a whole rank of the tensor, how do you selectively fill certain locations using that transformation to get back to the original tensor that format that you had? So yeah, so originally you had like an empty coordinate, right, that you showed that was filtered out because it didn't have any subtrees in your tensor, like it didn't have any subcoordinates, and so you turned it into another format, and you said there was a reverse transformation called fill to get it back, but you only selectively filled that one location, correct? Or is there a way for you to select? How do you select where you're filling in your coordinate tree as opposed to filling the entire the entire tensor? How does that work?
So you were mentioning the reverse operator of the tree.
Yeah, of the tree.
Oh, okay. So fill is doing basically the exact reverse schematic of the tree. It takes in a dimension level and it only fills in the Cartesian product of that dimension without touching other magnitudes and other dimensions.
you.